Alright, it seems to be that the video is live. My internet connection is a bit slow right now, so we'll see if this will be laggy or not. But looking at the work that needs to be done moving forward here, I have realized that there is really a need for some way of exchanging events between different parts of software, and primarily getting events from interrupts, and to have a clean way of delivering those events to different device drivers. And of course, this will be configurable over the device tree, and it has to be as resource constrained as possible. So I don't want to have a separate process for every timer, for example, where I would have event delivery done from that process, which is specific for a timer. But rather, I have been thinking about a system where I have an event object, which, or rather, more of an event dispatcher, where I can subscribe to different events and also broadcast events, both from processes and from interrupts as well. So I'll implement something like that right now, and we'll see how that works. So first of all, we need a new class, a new device class, which we're going to call events. Events device. We could call it events device, or maybe event device. I think events device is better. And this will include events header, and the header will, let's add events. I'm just going to copy this because it's too much for me to type. I'm lazy right now. Timestamp list driver, and this would be events, device, ops. Actually, I'm going to do like this. GPIO events. And this type of device will have a method for subscribing. So we can do subscribe events device, and it's going to be event. For now, I will just have uint32 events without any data. I will see if there is a need to have any kind of data pointer. At the moment, I think that this could be enough, because we are only interested in kind of delivering the notification. But we'll see. Maybe it would be useful to have some kind of data pointer as well. And it will also have publish and publish from ESR. Actually, I'm going to call this EV. Events device, event, and this will also take an int32 wake. This will be then sent to yield in the actual interrupt routine. Let's see. And then events subscribe, publish, and publish from ASR. Dev and also subscribe will obviously take like some kind of data structure here. Let's say this would be struct and this will have a list. head list, and this will also this will basically go into the list of subscribers, and then it may also have some kind of, it could have a data pointer, but I don't think it's necessary, because in this case we can just use container off. In this case, I think the only thing we need is actually just the method pointer. So int and this will be a global list of events, or rather, kind of, I will make it global, but it doesn't have to be global. It's just that many different drivers will use the same events interface. So there will be just one section in the device tree for this events driver, and then many different drivers will use that interface to interact among each other. So in this case, I will make it an int, and it will take a struct events subscriber, and int 32. Let's see, I can make this notify. That's a better name for it. Event. Okay, and all of the notifications here, they will be sent from the process that is responsible for this events, for this subscriber directory. So it will be possible to make to adjust the priority of this process, and by doing so, we can adjust priorities of different events and how they are handled. So, for example, for the motor update, I would have an event sent from the interrupt, from the timer update interrupt, and the delivery of that event has to happen very quickly. So probably I will make the event subscriber directory run at the highest priority, so that whenever timer update interrupt occurs, the RTOS switches to the task that is responsible for dispatching those events, and then any code that runs as part of the notification function will run in the context of this events process at the higher priority, of course. So subscribe, and we have, actually, let's see. So we are gonna want to subscribe to multiple events. So there will need to be some kind of internal structure for keeping track of the binding between the event and the subscriber. So let's see here. Publish event and publish from ESR. Dev sub and dev link. And then we declare the device class, and in events C, all we need is just events and driver, and define device class. events, and then I will also have a default implementation for the events. So I'm going to have, let's see, subscribe. Unfortunately, some of the device classes basically only end up featuring one single driver. That is a bit annoying for me, but it's currently the only way to get the device driver configurable from the device tree. So I have to make it into a driver. And device driver events probe and events remove. All of these methods should be static because they're not accessible. They shouldn't be accessible from outside. They're all going to be accessible through the ops object. I'm going to create the struct events, which will have struct events ops, device ops, dev, and it will have struct list add subscribers. List add. And I always forget, with this interface of Linux lists, I always forget the order of the, like, because it's backwards. It's like item is added to a list head, but it's kind of different with certain calls to this API, so it's a little confusing. But so I would kind of expect it to be like list add, and then the first argument is the list. But in this case, the first argument is the actual item that I'm adding, and the second argument is the list. So add this to self. Damn it. Let's see. Add the sub list to self list. Yeah, that should be correct. And then struct. And this will also have struct mutex, and this will have events self equals container of dev struct events dev ops, and then thread mutex. So whenever modifying lists, it's important to lock the structure, especially if we are iterating over the list, but also, of course, if we are adding to the list, because we could have iterations that will just go wrong if the list is modified while it's being iterated through. I think there is some kind of safe version of the. Actually, no. The safe version is only safe with regards to deletions. So it's possible to have a list that you can iterate through and delete from the list at the same time. But I don't think it's probably not safe against concurrent access anyway. But just to be on a safe side, I'm going to lock this. So lock and unlock this here, and we return 0. I should add some code here for checking if this event is already subscribed to by this subscriber, but I'll add it later. For now I can just return 0. Publish will go through all of the subscribers in the list. So this will be subscribers, and this will need to, let's see, how do I actually use this? Let's see, list for each entry, but then let's see. Position head member. Okay. So this will be struct events subscriber sub. So sub in self subscribers, and member is list. So if sub, let's see. No, actually, no. Actually, no. This subscriber list, I think. Let's see, struct events. I'll make this a list of bindings instead, so that I can have a subscriber. So a binding will have an event and a pointer to the subscriber. All right, and subscribe should then, let's see. So this will put a little constraint on subscribing. If I use dynamic memory here, if I allocate something here, the way that I have structured the dynamic memory allocation in my firmware is that I only allocate memory during initialization, and then it's never touched again. I think that memory allocation is a very flexible method to write very flexible code, but at the same time I don't want to allocate and deallocate. Like, I never want to deallocate anything during the runtime. So I prefer to allocate like buffers of objects and then use them during runtime, which kind of gives this predictable behavior for the software. Because there is so little memory on these chips that any kind of fragmentation can be it can create very undefined behaviors. So if I use memory allocation here, then, which kind of makes sense, like subscriptions are going to be done in probe methods, and then once they're set up, they basically run for the rest of for as long as the firmware runs. So I think it's a constraint that that is possible to live with in this situation. So let's create events binding. And EVB, let's see, init list head, EVB list, and EVB event is event, and EVB sub is sub. And then we can add this binding here. And then if, so this is going to be very simple. If event is equals to the event being published, then we call the subscriber method. So then we do like this. So if that and, let's see, EVB sub and EVB sub notify. Now we call EVB sub notify with EVB sub as the first argument, and then event, like this. And actually, yeah, so this is actually going to be happening in the process, which will be set up in the, let's see, so in the probe method, events probe, void fdt int fdt node. Here I will set up a process for, so this will actually run as part of the task. Let's see. Static void events dispatcher. So this will actually just sit and wait for the queue. Let's see. Self equals events ptr, and then thread queue receive self events, and this will receive into the EV if I've received an event, then we dispatch it. And this will just wait forever until next event arrives. So I think this nicely breaks out this functionality so that it can be shared among different drivers. I think this will be very useful. And then here I will do thread create, and first of all it's going to be uint32, no, actually uint8, priority fdt get int or default fdt node priority, and priority would be 1 by default, I guess. I could set it to 1. And then there will also be uint8, or actually uint32 stack size. Let's make this 450 by default. So this is something I can also check here then. This is the actual number of bytes left on like from the stack, from the reserved stack. This is the number of bytes left. So if any one of these numbers goes below 100, then I should increase the stack size. Let's see. And this will create a new process here, which will, let's see, name stack pointer priority. So this will be events dispatcher. Let's see what else. Thread name stack pointer priority. Stack pointer priority and null. Okay. And then here, so yeah, also in the probe method, I will create this object. So I'll do like this. Self is allocate size of struct events, and then let's see, thread queue init events self events, and then this will be number of elements. I'm going to make that configurable as well. I think 8 would be enough. So queue size, 8 would be the default value for the number of elements. Let's make this stack size. Priority stack size, queue size. And size of units 32. Okay. And then let's see. Also I need to, let's see. This will not be ops. This will be device. Like this. So, and then I also need to initialize the mutex. And actually, I don't need a mutex because I'm using this queue now. So essentially, or maybe I still need the mutex. Actually, I still need the mutex for the list. Yeah. So this still needs to be protected. And then I have to keep it locked until I'm done with it. But then in publish here, I don't really need to have any. I don't think I need to have any mutex there. So publish will just do like this. So return thread queue send struct events self equals container of here. Send self queue self events and this will do the same, but just also supply wake and call send from ESR. Okay. And then I need to initialize the mutex. And init list head. Okay. And I will also do events device init. Events device register. Initialization takes the FDT and FDT node for this device so that it gets saved. And this is then used to find the devices by the FDT node, which is something that's used a lot for things that are referenced. So any reference in the device tree actually points to an FDT node, and having this node saved in the base structure of the device class helps find a particular instance of a device driver that is responsible for that particular node in the device tree. And this will also point then to ops here. So this will be events ops. And events ops will be defined here. So static const struct events ops, events device ops, events ops equals subscribe equals events subscribe, publish events publish, publish from ESR equals events publish from ESR. And now I can create this driver in my device tree. So I'm going to go to DTS, and I'm going to test it with the timer interrupt. So I will add this events driver at the top, compatible. And this will actually also be a reference. That's compatible. That's the default one. And then we can have the reference to it in the application. So this will be events here. Events. So this is the reference for the subscriber, the application, and also I will have, let's see, for the timer I will also provide the reference for the events publisher, but also I need to specify which events I will be sending from the timer. So I have to think about a good way of doing that, and I think I have an idea for that. Let's add this events here. This will be for timer 1 and timer 8, because these are the timers that are responsible for generating the PWM for the motors. And maybe I could do it something like this. Let's see. So as a subsection with publisher and update would be, and this would be a global definition, so FB motor 1 timer update. This could actually be an interesting way of doing it. So then I don't have to type events publisher, events update, things like that. It just becomes less messy. And for the team 8, we'll have a similar structure, and here it will say motor 2. And then I need to also add a header file for the device tree here. This will be application-specific stuff. I'll just put it here. So define, or actually it's going to be an enum. Enum FB event motor 1 update, and also motor 2 update. And it will start on 1. So 0 is an invalid event. Okay. And this will be global for the device tree, really. So any the actual codes of the events are going to be programmed through one of these event sections. Let's see. And now I just need to add support for the for publishing events and parsing that section into the timer driver. So Tim C, and here I'm going to check how I did on the GPI driver. So I'm not sure really how to get the subnode. Maybe I can just search for subnode here. Subnode. Actually, I'm going to check my loader driver here. Oh, so for each subnode. That was simple. So for each, let's see. First I actually need to get the node. Then I need to get it by name. Find a subnode, okay, based on substring. Okay. Subnode offset. Oh, yeah, subnode offset. That's it. So this is how I'm going to do this. So actually, it's a lot simpler than I thought. It's going to be like this. And what does it return if it doesn't find? Return less than 0 then. Yeah. And then here, if events, then I can find right events device publisher equals find by ref fdt. And in this case, it's going to be the events node, and the reference will be publisher. If not publisher, okay. Actually, I will return 0 there because I don't want this to be, or actually, I'll return -1. But the device driver for this timer will actually be registered already, if it is registered with. So yeah, this is not good. This is not good. I'm gonna do this up here. I'm gonna validate this section first. So if, let's see, if events, then I'll set the publisher. Yeah. And then stack, let's see, and update. And for now, I only have one event, which is the update event. Great. And then at the end here, I can just check if, let's see, if publisher, then we register events, subscribe. No, actually, do we even need to do anything here? Oh, not really. So this is actually not necessary. The only thing that I'm going to do is save this publisher, the pointer to the publisher. Let's see. Do I actually have a structure here? Yes, I do. Where is it created? Here. So self, publisher, publisher. I'm going to evaluate this method of doing it, and the only thing that I'm, or actually the main thing that I'm concerned about is how fast is it going to be? Like, will it be able to meet the real-time constraints when the interrupt will have to wake up a task and then that task will execute the actual code for example, for the current control. Will it be fast enough? And that's a question that I can only answer by actually testing it and checking what is the actual delay between the event happening and the handler being run. And I can measure that. So the first step is to just implement something and then test it, and then we'll know if this is a good way of doing it. So event publisher, and then I just need to add the interrupt handler here. I already have the interrupt handler, and then let's see. So timers. I'm just going to make sure that it's the right index. Team 8 is going to be number 7. So let's see. Up. Thank you. Now this is. What the hell is this? Why did I get GPI? Let's see here. So if it was the update event, then we can do like this. Events publish from ESR and int 32 wake equals 0. Self publisher. And thread yield from ESR. Let's see. And actually, I'm going to update this method. Events here. This is just to get the syntax such that this is going to be while 0, so that it behaves essentially the same way in code as a call like this. I can put a semicolon after this, and the compiler will not complain. And if I have an if statement, it can actually create errors because, like, imagine if there is some else statement that's not supposed to be there, then that becomes part of the if statement. So if I enclose this into do while, then I eliminate any chance of this macro resulting in faulty code. So let's do this do, and then if def. Okay. So now I can just call it from my timer code without worrying that publisher may not be set. So publisher could be 0, but now it doesn't matter. And then I have this one as well. So I'm going to do the same thing here. Number 8, so index number 7, and then the same way of publishing it. So, yeah, it's actually going to be the same code. And what is this? This is not correct. Like this. And then in my application code, so if I go to main, I will write a handler that will run in thread context. So it will be able to sleep, it will be able to do anything that any process can do without worrying about whether it's running in interrupt or in process context. So process and thread is basically the same thing. They are pretty much the same thing in Linux, so I use them. I use the names interchangeably, and especially on an RTOS like this, each thread is basically considered to be a process. So the next step here is that I wanna actually subscribe to this event. So I will. Let's see. This will be a weird include path. The file is located in DTS folder. Okay, it will have to be a weird include path for now. So I need to add a handler for this first, which will be in the application object. This application object is getting really big now. And then in probe method, probe, let's see. First of all, I'll get the events device. Events. And then if not events, then it's an error. Or is it? Actually, events is not critical, I think. At least not right now. So events will just be saved here. Self events equals events. And then events will need to be registered here. So events subscribe. And I'm going to have a method here for initializing the subscriber, even though there is um, just one member in the structure. Making this a method guarantees that if I add more members and I update this, the prototype of this init function, then I will know where this structure is being populated, so I can update all the code that uses it. If I just manually fill in the structure with like notify and just set it to a pointer, then if I add more members to this structure, I will not know that there is some code that is now broken because all of the fields are not populated. So it's good to have a method for initialization. And this will then take, let's see, events handler, and this will subscribe to FB event motor 1 update and then motor 2 update. Cool. So now I can even do things like printing to the console from the event handlers, which is going to be very CPU intensive if the update event is fired at 30,000 times per second, so it's never going to actually work at the same speed. It will actually starve all of the other threads if this event dispatcher is running at maximum priority. But what I could do is toggle a GPIO, for example, and that's much faster. And that will allow me to measure the actual delay time between the update event actually firing on the timer and the update event being handled by the application code. So FB events handler, that's something I need to add. I think this should be a void. No reason to have it. To have it as an int. So struct application is container of sub struct application sub. Let's see if this is actually working. So print k. So this should be printing 1 and 2. Let's get it compiled. Oh, of course. Wake. Publish from ASR wake. Next is I need to include events here. And this needs to be included as well. So So I'm going to add both the C file and the include file here, so that they get installed properly. Let's see. And I wonder what GPIO pin I'll use for measuring the timing. I need 2 pins actually, and it has to be pins that are directly connected to the microprocessor. So let's see if there is anything that's available. Declare device class. WebDT. Actually, it's time to include libwebdt directly into driver here. Initialization from incompatible pointer type. So in what way is this incompatible? So events is, let's see, events device ops, subscriber. And then this should have the events device ops. Device. Why is this incompatible pointer type? Maybe could events somehow be actually struct events is defined here. Let's see. timeout how much to wait when publishing an event from a process. This does not apply to interrupt handlers, but we could say default could be 100 milliseconds. So self timeout equals timeout. And now it's only the container off that's not really working. If you are this to receive, this also has timeout. This is events binding for iterating the list. Next, let's see. Events remove. That is not implemented. There's still a problem with this container off. Why is it a problem? Events device. Let's see. What am I missing here? Why does container off complain? Oh, wait. Of course. It actually says dev here. It's supposed to be dev ops. So dev ops. Of course. Yeah, and also I'll include this. file with the definitions. It's actually located. Let's see, one step up again. Where can it be? So we have one, two, three DTS. Maybe I can include this. See if this works. Actually, this should point to like source directory or something. Let's see. This is gonna be tricky because this is outside of the source tree. So yeah, I'm gonna copy this for now. Yeah, I have to do a little review of that. Let's do like this. This will not reside here because I don't want to have a copy of the same file. Let's see, now I can just compile it. So event subscriber handler. Container off. Actually, this will be okay, I'm gonna leave it at events for now. And then it's subscriber image. I know I could type def that, but I think it's more readable when it's not type def. So this will do mem set self 0 size of self and self notify is notify like that. Let's see the builds now. Okay, syntax error in device tree. Of course, this is not usable because this is only preprocessor, so I cannot use that kind of stuff. I have to have defines. See if the event system works. Alright. Events not specified but no publisher. Interesting. This shouldn't have events node. Let's see. Okay. If events more than 0. That's the correct way of checking this. Because this will be -1. So if I do if events, it will actually be true every single time. So let's compile this again Okay, and we're actually getting the update. Cool, it's actually working. Number 1 is missing, presumably because it never actually gets to run. I think what is happening is probably that the timer update is kind of okay. I'm not going to speculate because this could be anything. It could be a problem with any part of this path from the update interrupt to the actual receiver. But at least one of them is working. At least timer 8 update is working. Maybe I could do like this actually. Let's see. One of the ways to check if both of them are working is if I add a counter which counts number of calls to that method, and then I just print out the counter. But I think that's kind of useless. I think it's more interesting to find out how much delay is there between the timer interrupt. Hey. Between the timer interrupt and the actual event being delivered. So I'm gonna look at that in the next video. I think this video is getting quite long now, so I'm gonna stop this video and I'll continue in the next video. And thanks for watching. My dog is saying hi.